HLAA vectors, day number 4. Today our topic is the equation of a line in both 2 and 3 dimensions. Below you're going to see 3 forms, equations defined using a direction vector and a point on a line. So we're very familiar with finding the equation of a line using point-slope form, right? And point-slope uses a point and a slope. Really a direction vector, all that is a vector that tells you slope of the line. Okay, so 3 forms. One is vector form. You'll see it in this form. xy is equal to x1 plus y1 plus lambda delta 1 delta 2. And this right here, all right, x1, y1 is your point given. d1, d2 is your slope. Now, slope is kind of hidden in this, in that your slope is actually going to be equal to the change in y over the change in x. Okay, so d1 is really your change in y, d2 is your change in y, and d1 is your change in x. Okay, and then this lambda thing, this is just a parameter placed on the direction. So if I want to get from one point to another, lambda might change depending on how far I want to travel. Okay, we're going to talk a little bit about parametric form, which is an adaptation of vector form, as well as Cartesian form. Okay, so let's get into a few examples. Okay, let's start here in this example with a line in 2 dimensions, of course, on the xy plane. Okay, and what do we want to do in part A is to write the vector equation of a line that passes through A and B. All right, so we're going to make the assumption that this line, let's call it L1, which I'm going to denote as xy. Okay, this can also be denoted as R, and I'll show you there's really no difference between the two of those labels. Okay, but line 1, right, denoted xy, is going to pass through point A and travel lambda steps in the direction of B. Okay, so this is our point, as noted before. And we're saying that the vector equation of this line starts at A and heads toward B. So how do I find this direction vector, right? This would be the direction vector AB. Okay, so to find AB, what we do is we take the points of B minus the points of A, where you're headed minus where you came from. Okay, so that would be -1 minus 2 and 2 minus a -3. So that direction vector would be the vector -3, 5. Okay, so this would be the vector equation of this line. Let's talk about what this means. This line, xy, or r, right, and r could be equal to all of this stuff up here, starts at the point A, 2, -3, travels left 3 units and up 5 units. And we could find another point, right? So if we did lambda equals 1, then we would end up at B. If we did lambda equals 2, we'd end up twice as far as B, right? So this xy is just where we end up after lambda steps in this direction. Okay, so let's visualize this. All right, let's put A and B on this coordinate grid xy plane. Okay, so here is A. A is at the point 2, -3. I stated earlier that if we went left 3 and up 5, we would end up at the point B. Okay, so let's put the point B in green, so that would be -1, +2. There's the point B, -1, +2. Okay, so what this direction vector from A to B would equal is we started at A, we headed in this direction, 1, 2, 3 units left, and 1, 2, 3, 4, 5 units up. So if lambda equals 1, we would end up here at B. Okay, now we could change lambda. Lambda could be -1. If lambda was -1, this vector would head the same distance in the opposite direction. This would be lambda equals -1. All right, let's take a look at part B. All right, so part B, finding the Cartesian equation of a line. What you want to do is you want to go from vector form to parametric form, and from parametric form to Cartesian. So in this example, I'll show you how to find parametric form as well. Well, parametric form is really easy to find from vector form. So I take the form that I have in part A, and I put it in parametric form. Okay, so let's put it in this form. That'll be x equals 2 minus 3 lambda, and y equals negative 3 plus 5 lambda. Now that's parametric form. What I want to do is I want to take that and I want to put it in Cartesian form. Cartesian form, parametric form, and vector form, or vector equation, are all useful in different scenarios. Okay, so let's go ahead, and what I'm going to do is I'm going to solve for lambda. I'm going to solve for lambda in each case. All right, so if I take x and I solve for lambda, right, I would subtract 2, divide by a negative 3. So that'd be x minus 2 over negative 3. If I did the same thing for y, solving for lambda, I'd add 3 and divide by 5. So y plus 3 divided by 5. Now I've found lambda for each of them. Therefore, I've now found the Cartesian equation for this line. Okay, there you go. You've got Cartesian equation for that line. Let's look at part C real quick, which is interesting, which applies to everything we've now looked at. Okay, so part C says, come up with the slope-intercept equation of this particular line. Well, in order to come up with the slope-intercept form, or slope-intercept equation, what I need is two things. I need the slope. Well, we know the slope as the change in y over the change in x. And we talked about that in previous on the previous slide, actually. So our change in y of this vector, change in y is 5, and our change in x is negative 3. So the slope of this particular line is negative 5/3. Okay, I can have the negative wherever I want it, doesn't really matter. When it comes to the y-intercept, we know that the y-intercept occurs when x equals 0. So the y-intercept is going to be whatever that value comes out to be when I plug a 0 in for x. So I'm going to go ahead and do that. I'm going to utilize my parametric form for this portion. And I'm going to plug a 0 in for x. And I'm going to solve for lambda. So if I plug a 0 in for x, I get 0 equals 2 minus 3 lambda. That tells me that lambda equals 2/3 when x equals 0. Well, if lambda equals 2/3 when x equals 0, what would y equal when lambda equals 2/3? So I'd plug in a 2/3 for lambda, and I'd solve. Well, this would be negative 9/3 plus 10/3, so it looks like y would equal 1/3. So I've now got my y-intercept, and I've got my slope, so I can write the slope-intercept equation for this line. Remember, y equals mx plus b. B in this case is this 1/3. It's the y value when x is 0. Therefore, the slope-intercept equation would be negative 5/3 x plus 1/3. If I look back up at my graph, that looks like I was pretty close. The accuracy of my graph was pretty good. My dog's whining. Okay. A little human error there, but that is the slope-intercept equation of that line. All right, let's continue with the next slide. Okay, let's talk about a normal vector. If two vectors are perpendicular to each other, we could say that one is the normal to the other. So let's say AB, its scalar product with BC is 0. Well, then I could say that BC is the normal vector to AB, okay? So let's talk a little bit about that in this context here. So find the vector equation of the line passing through this point satisfying the following. That it has, I should rewrite these notes, but that it has direction vector 2I minus j. Okay, so all that means in part A is that I'd write that this vector, okay, a vector equation of a line passing through negative 3, 4 with a direction of 2 minus 1, right? That would be satisfying part A. Boom. Passes through negative 3, 4, has a direction of 2, negative 1. Okay, part B. Part B is asking for us to draw or to write the vector equation of a line that passes through negative 3, 4, and its normal vector is 3i plus 5j. So that means that the vector I'm about to write out has a slope that's perpendicular to this direction vector. All right, so the normal vector to this vector I'm about to talk about is 3, 5. Okay, so that means the slope of the normal vector is equal to 5/3. Well, two vectors or two lines are perpendicular if their slopes are opposite reciprocals. So the slope of the vector I'm about to talk about, I'll just call it m, should be the opposite reciprocal. So this would then be the change in y, and this would then be the change in x. Now, it doesn't really matter where you put the negative in this case. It could be in the denominator or the numerator. So let me call this vector t, which would pass through 3, 4. I'm going to use a different parameter, say mu in this case, and I would have a change in x of 5 and a change in y of negative 3. So take a look at how these two vectors compare, right? Negative 3, positive 3. That's the difference between change in y and change in x. And positive 5, positive 5. Now, we only change the sign on one of the values. It doesn't matter. But if I took oops, change back to a pen. There we go. If I took direction vector, oops, didn't want negative there. How about positive 5, negative 3, which is found in this vector. I took the scalar product with 3, 5. I'd end up getting 15 minus 15, and clearly their scalar product is 0. Thus, vector t is perpendicular to this normal vector, right? And I could have called this normal vector whatever I wanted to. I could have called it q, whatever. But I chose to call it the normal vector. And I should say it's the normal vector to t. Okay, let's look at another example. Okay, here is where we first encounter two lines and wanting to find their point of intersection. Okay, so I'm told that these two lines intersect. That means they would not be parallel and they would not be the same line. Okay, so the first thing that you want to do is put each of these in parametric form. So I'm going to take line 1, which you can see here, and I'm going to put it in parametric form. If you got questions about how I get here, please make sure and ask in class, okay? But all I'm doing is solving for lambda. Now, it might be helpful if you put that in vector equation form first. So maybe I'll do that for this first example. I could write r is equal to 2, negative 5 plus lambda, negative 1, 3. And then you can put that into parametric form from there. Okay, so let's do the same for L2, our second line. Our second line, we're going to use a separate parameter. Okay, we can't assume that they're on the same parameter, but later on we might be able to if we can see something special. Okay, and it looks like x would equal negative 2 plus 3 mu, and y would equal 1 minus mu. Okay, so you can tell this is in 2 dimensions because you only have an x and a y component. Okay, so what I want to do is I want to find the point where my x's are equal. I want to isolate these, right? So I'm going to set 2 minus lambda equal to negative 2 plus 3 mu. Now, I won't necessarily be able to find out where their x's are equal yet, right? What I'm trying to do is eliminate one of the parameters. Okay, so what I'm going to do is I'm going to solve for lambda here, and I'm going to use that when I look at the intersection of my y values. Okay, so if I solve for lambda, I'd subtract 2 and multiply by negative 1. So that would give me 4 minus 3 mu. Okay, so lambda and mu have this relationship going on. Now I'm going to go over to my y values, set the y's equal, which is negative 5 plus 3 lambda equal to 1 minus mu. And what I'm going to do is I'm going to plug in lambda from right here. I'm going to plug that in for lambda here. What that'll help me do is eliminate that lambda parameter and have everything just in terms of mu. So I'm going to plug in a 4 minus 3 mu. Okay, and I'm going to solve. And if you solve that, what you'd end up getting is that mu is equal to 1. Okay, so these two y values, right, are equal when mu is equal to 1. Let's find out the lambda value for which that is true. So I'm going to take mu, I'm going to plug it back in up here. So lambda equals 4 minus 3 times mu. It looks like these two lines intersect when both lambda is equal to 1 and mu is equal to 1. So let me write that out. So L1 intersects L2 when lambda is equal to 1 and so is mu. Now, this is a very interesting situation. I'll talk about the importance of it in a moment. What I can do then is I can plug 1 back in for either lambda and find xy, or mu and find xy, or I can identify which x value is easier to work with, which would be that one, and which y value would be easier to work with, which would be that one. So I'm going to take my L1 x value, just because of the algebra. It's just easier to use, and I'm going to plug in lambda there. Okay, so what was lambda? Lambda was 1. Okay, so it looks like our x value will equal 1. Okay, so the point of intersection of L1 and L2 is at x equals 1. Now we just got to find y. So my y value will be 1 minus mu. Mu also happens to be 1, and therefore my y value is 0. Thus, the point of intersection, L1 and L2, intersect at the point 1, 0. Okay, now, interesting thing, something to note. Okay, lambda and mu are really parameters, right? So later on when we get to applications, okay, and it's not useful yet, but when we get to applications, what this means is if the two lines intersect as they do above, if lambda is equal to mu, then we have collision. So like you could be talking about submarines, you could be talking about boats, you could be talking about airplanes and aircraft, right? If lambda and mu are not equal, then sure, their paths intersect, but they might not collide. Okay, but there's no collision. Very interesting. Okay, that'll come up later in future lessons. All right, let's continue. Okay, so here comes up this idea of relationships of lines in 2 dimensions. Okay, so if I have a flat piece of paper, I don't know many pieces of paper that aren't flat, but if I have a piece of paper, which could be a plane, right, 2-dimensional plane, and I draw 2 lines, there's 3 options, right? The 3 options are the lines are parallel, okay, so they don't intersect. Here's option 1. Boom, line 1, line 2, never intersect. Okay, option 2 is that I get lines that intersect, and they can intersect at right angles or non-right angles, right? Option 3 is that we have the same line. So line 1 and line 2 are exactly the same line. So they have the same direction vector and can include all the same points. Okay, so let's take a look at the example below and determine whether the following lines are concurrent, and if not, classify them differently. Okay, so the first thing that I could do to determine that these lines are concurrent or not is to see their direction vectors. If they all have the same direction vector or a scale of the same direction vector, then they could possibly be concurrent. So let's take a look at L1. All right, so I'm going to write L1 in parametric form. Okay, so I see L1, -5, 2 lambda. Okay, that's my x value. My y would be 6 minus 3 lambda. Okay, you can start to kind of see how this process is done. Okay, for L2, I get x equals 1 plus 2 mu. I got to use a different parameter. And y is equal to -1 plus 3 mu. Okay, I can already actually tell, here's the direction vector of the first, it's 2, -3. Here's the direction vector of the second, it's 2, 3. that means the slope of L1 is equal to -3/2, and the slope of L2 is equal to 3/2. So clearly I can tell that these vectors are not parallel, right? At least L1 and L2 are. And actually looking at them, I can see that they're not perpendicular either, right? If this was 2/3, I could see that they're perpendicular. Let's go a little further and then we'll look at classifying this. Okay, L3, this is an interesting form, right? This is called standard form. What I'm going to do is I'm going to put it in slope-intercept form. So I'm just going to solve for y. So I'm going to solve for y by doing the following. Subtracting 3x and dividing by 2. So I can see the slope of L3 is equal to -3/2. So it looks like L3 and L1 are parallel. L1 is parallel to L3, so let's sketch those. All right, let's go L1 in red. I'm gonna just kind of ballpark these sketches, right? Let's see here. So L1 and L3, -3/2. I don't know if the orientation of these are correct, but that's okay. I don't really care. I'm just trying to visualize these. These are parallel. And then I can see that I know that this green line, L2, is not going to be perpendicular, so it might intersect something like this, right? Here is L2. Okay, so how would we classify these? Well, we would say that, you know, L1 and L2 are intersecting lines. I can see that right here. L2 and L3 are intersecting lines right here. And L1 and L3 are parallel. Now, one thing we haven't considered yet is it possible that L1 and L3 are concurrent, right? Is it possible that I just, based on my human mind, decided to sketch them as parallel because they had direction vectors that were equal? Potentially. What I could do is I could see if this point, -5, 6, satisfied L3. So let's do that real quick and make sure and classify whether or not L1 and L3 are concurrent. Okay, so I'd put the point 6 in for y. Excuse me. Let's do this. Let's do it this way. Let's plug in a -5 in for x and see if we get 6 out. Okay, so let's see now. That'd be a +15 minus a 3 over 2. And look at that. It actually does work. So L1 and L3, even though I sketched them as parallel, they're actually the same line. Okay, they contain all the same points. Since they're parallel and contain at least one similar point, they have to be concurrent. So we could say that L1 and L3, no, they're not parallel. L1 and L3 are concurrent. Okay, let's continue on to the next slide here. All right, let's go with some 3D space here. You can tell that this is 3D space because we have an x, y, and a z coordinate. We're going to draw or write out the vector equation of this line in a very similar fashion that we did with example 1 for the day. Okay, so I'm going to draw out a vector equation, x, y, z. I want this to go through A, 1, 0, -4, in the direction of B. So to get the direction vector from A to B, right, I take the values of B, which are -3 and 1 and -2, and I subtract the values of A, which are 1, 0, and -4. Okay, this is going to give me my direction vector from A to B, which is -4 and 1 and a 2. All right, so there's the vector equation of that line. Oops, that should be a +2. Okay, part B says find the Cartesian equation of the line. Okay, so I'm going to put this in parametric form, which would be x equals 1 minus 4 lambda. Y equals, that's a nice one, lambda. Z is equal to -4 plus 2 lambda. All right, I'm going to solve for lambda. Well, in this case, lambda ends up equaling x minus 1 over -4. In the second case, for y, lambda just equals y. And in the third case, it looks like lambda equals z plus 4 over 2. Thus, if I set all the values together equal to each other, I would get x minus 1 over -4 is equal to y is equal to z plus 4 over 2. And there is your Cartesian equation of that three-dimensional line. All right, let's keep going. Okay, in our next example, what we're going to see is a line in 3 dimensions, okay, and kind of formatted differently. So here is our x components, right? That has the x coordinate and the direction combined in that parenthesis, then the y, and then the z. Very interesting. Okay, so what I'm going to do here in this example is I'm going to show that L does not contain, this line does not contain the point D. Okay, so the first thing that I want to do is I want to write this in parametric form. So I'm going to write x as 1 minus lambda. Okay, you can see it right there. Y is equal to 2 plus 3 lambda. And z is equal to 0 plus 2 lambda. There should be a 2 there. How about a 2? There we go. Okay, you can see each of those components showing up attached to I, j, and k. All right, so what I want to do is I'm gonna use point D, right? And point D is the point 1 to negative 3. And I'm going to set it equal to 1, 2, 0 plus lambda times 1, 3, 2. Okay, so in essence, I just put this in a vector equation, and what I want to do is I want to solve for lambda. Okay, so this is right here. This is point, this is point D. If D is in this line, right, or if L contains D, then lambda should be exactly the same for all 3 dimensions. Okay, so I'm going to set 1 equal to 1 plus lambda. That's my x's. For my y's, I'm going to set 2 equal to 2 plus 3 lambda. And for my z's, I'm going to set negative 3 equal to 0 plus 2 lambda. And I'm going to solve for lambda. If they all come out to be the same, D is contained in L. All right, so clearly it looks like lambda is 0 for the x's. So all the x's align for point D, right? Or the x aligns for point D when lambda equals 0. The y's align for point D when lambda equals 0 as well. However, the z's only align if lambda equals negative 3 halves. Thus, therefore, D is not contained in L. Okay, perfect. Let's look at part B here. Find the vector equation of the line parallel to L that passes through D. Okay, so I'm gonna call this this line that's parallel to L. I'll call it how about L2? Okay, L2 we can say is XYZ, right, and passes through D, which would be 1, 2, negative 3. I'm going to use a different parameter. We'll go mu. And if it's parallel to L, then we want its direction vector to be the same as the direction vector for L, 1, 3, 2. Okay, so this is how I would get myself a line that contains D that's parallel to L. All right, guys, let's continue to our last example. Actually, I think I goofed something up here. Yep, I sure did. Let me go back here. It didn't affect anything with regards to the previous example, but there should have been a negative 1 here. All right, I see a negative 1 there. So that should have been a negative 1, which would have made this a negative lambda, which wouldn't have changed this value. So it doesn't really change anything with regards to the example other than I was just slightly inaccurate there. All right, let's continue to the last example. All right, so before we get to the last example, I forgot I have to kind of lay some things out for relationships of 3-dimensional lines. Okay, so 4 possible relationships, right? The first of which is parallel. Here, L1, L2 are parallel. Never intersect, okay? Option 2, we have intersecting lines in 3 dimensions. Now, it's hard to see depth-wise, but those 2 would intersect, or they could intersect at a 90, right? So they could be intersecting perpendicular, intersecting non-perpendicular. We could have concurrent lines like we did in 2 dimensions, right? One line and the other line are exactly the same, containing infinitely many points that they share. The third option is skew, and skew is non-parallel, non-intersecting. So let's say I have a line like this, and I have another line that's not parallel to it but doesn't intersect it. So you can't see it, but this green line is above the black line. We just don't have the perception to be able to see it. So if I looked at it from the side, right, if I were like flat on the surface on my belly looking at these two lines, right, I would see like a green point. If I looked right down, right, if I looked right at the green line, and then I'd see a black line underneath it, right? So this green line would be kind of coming at you and heading in the direction away from you as well. Okay, those are called skew, non-parallel, non-intersecting. Let's talk about that in the next slide, and we'll be finished for today's notes. Okay, so show that the following lines are skew. That means, like I said before, I want to show that they are non-parallel and that they are non-intersecting. Okay, I'll abbreviate that. All right, so let's take the first idea of non-parallel. So if two lines are non-parallel, right, then their direction vectors are not scalar versions of each other. What I mean by that is like 1, 2, that's a direction vector. That would be parallel to -5, -10, right? Because the first is equal to a scaled version of the second, right? Okay, so those would be parallel or potentially concurrent depending on the situation, right? But at least they have an equivalent direction vector, right? These two would be non-parallel. Okay, so how about 1, 2, and 4, -8? Those are not parallel. They can't be parallel, right? Because you can't scale 4, -8 to be equivalent to 1, 2, right? So there is no value k that I could multiply by 1, 2 to make it equal to 4, -8. All right, so that's how we're going to go ahead and show that these two are non-parallel. So I'm going to put the first and the second lines, I'll call this L1, in parametric form. Parametric form is like really, really helpful, so get used to using that. So my x is 1 plus 3 lambda. My y's, -2 plus 2 lambda. My z's will just be lambda. Okay, for L2, I would have x equal to, using a different parameter, -3 minus 2 mu. My y's, 3 mu, and my z, 2 plus 4 mu. So I'm going to look at the direction vectors attached. So the direction vector for line 1 is 3, 2, 1. The direction vector of line 2, -2, 3, 4. Those are not scaled versions of each other. Okay, so this cannot equal some constant k, which is in the real numbers, times the second direction vector. Okay, therefore, L1 and L2 are not parallel. All right, so we can kind of check that off of our checklist for skew definition. Okay, not parallel, check. Now we have to show they're non-intersecting. Okay, so in this case, very like what we've done before, is we want to lay out, of course, their parametric versions, right? So we're going to take their x's, set them equal, their y's, same thing, and their z's, same thing. Now I'm going to pick the one that's easiest to work with, which looks like it's going to be the z's, right? Lambda equals 2 plus 4 mu. I mean, I've already got lambda then, right? You can overcomplicate it and work through others and get, massive fraction algebra work, but I would go with the z's to start. Okay, so I've kind of set that in motion. Okay, so now what I think I might do is let's set the x's equal 1 plus 3 lambda, set equal to -3 minus 2 mu, right? That's right here. I'm setting these two x's equal, and I want to find the parameters lambda and mu such that these two potentially intersect. But what I'm trying to do is show that they don't. So let's continue mission here. So I'm going to take lambda equal to 2 plus 4 mu, and I'm going to plug it in for lambda right here. Okay, now I just have two equations, two unknowns. Actually, one equation, one unknown now. I had 2 and 2, but now I'm going to be in a better situation. Okay, so that would be 1 plus 6, which is 7, plus 12 mu is equal to negative 3 minus 2 mu. Okay, so that would equal 10 mu is equal to negative 10, which means that mu equals negative 1. Okay, I like that. So when mu equals negative 1, lambda, let's see, what does lambda equal? Lambda equals, looks like a negative 2. Okay, so I'm hoping that the y values are equal I'm trying to show this is skew. So when I plug lambda equals negative 2 into the y for L1 and mu equal to negative 1 for the y in L2, if those two values are not equal, then we know the lines do not intersect. So let's do that. And I might have said that a little quickly, but I'm going to plug lambda equals negative 2 into lambda for the y value for L1. Okay, so let's do that. So our y value for L1 will be negative 2 plus 2 times lambda, which is negative 2. Okay, so that y value will equal, what is that, negative 6. Okay, and for L2, I'm going to plug in negative 1 for mu right here. And it looks like, y equals 3 times negative 1. So y equals negative 3. Well, clearly, negative 3 is not equal to negative 6. Since that's true, right, I know that and let's clarify this, x for L1 is equal to x for L2. And y for L1 is equal to y for L2 when x is equal to, when lambda is equal to negative 2 and mu is equal to negative 1. However, the z for L1 is not equal to the z for L2 when lambda is equal to negative 2 and mu is equal to negative 1. Therefore, L1 and L2 do not intersect. Thus, they are skew, right? So long example, but I showed that these two lines were non-parallel, non-intersecting, and therefore they have to be skew. All right, guys, that's it for this lesson. Kind of a long one, but we'll get some time in later on to work through some problems. So we'll see you in the next video.